So CX 113 video review for the final, section 6. So in section 6 we have a few short questions to answer, and we'll just go quickly talk over them, and I don't have any text for these. So in sorting algorithms, when you do comparisons and swapping, which is more expensive computationally? So comparisons versus swapping, and explain. Depending on how you answer this, you could actually answer in either way. However, if you're kind of going through our class and using Java as the language, typically when we do swapping, we're just changing addresses of pointers. So pointers are either 4 or 8 bytes, so pretty small in data. Whereas comparisons, if they're objects, can be quite large depending on how many elements you're comparing and stuff like that. So typically we would say comparisons are more expensive than swapping. However, it depends on more explicitly how the language handles the two different operations. In swapping, if we're having to copy lots of pieces of memory over from one place to another, then that would obviously require more time as we have to copy bigger pieces of data over. So it really depends. I would take either answer as long as you kind of explain the idea behind what a comparison and swap is and what you're comparing it to for each of the two things. So just keep that in mind. Again, Java, typically swapping will be quicker than comparisons just to the objects and what we have to exchange, whereas languages like C++, we can swap whole blocks of memory, and that can take a lot of time to do that, whereas a comparison can be pretty quick. Question 2, what is the difference between breadth first search and depth first search? So breadth first search, you start at a node or the root, and you kind of go level by level. So each step away from a node, you're going another level down typically. So for example, in a tree, if we start at the top root, we'll go down one level, look at the 2 nodes there, then we'll go down to the next one and look at the 4 nodes connected to the 2 nodes that we just had looked at. So it kind of goes level by level, and by the time you get to the bottom, we will have covered all the nodes in the tree. Whereas depth first search, what that does is it keeps going in one direction until it finds where it can't go anymore, and then it goes back and will then try a different direction if there's ways. So it goes all the way down to the bottom first, and then so it finds one route quickly, and then the remaining routes eventually come out of that from where it goes in the tree. So number 3 is what is the runtime complexity of the following operations for hash map, insertion, removal, and lookup? So insertion, removal, and lookup are going to be all O to the 1. However, we should note that insertion, if we have to do a rehash in there, the amortized cost of that is all basically comes down to 1 after you kind of rehash and everything like that. Also, hash maps needs to have a relatively clean table, depending on the approaches. So our threshold for rehashing needs to be set up appropriately so that we can handle that and not have too many collisions in our hash table. The runtime complexity for a binary search tree for insertion, removal, and lookup. Again, these are all log n typically. However, it doesn't say if the binary search tree is balanced or not. So if we have a nice balanced search tree, then that is true of the log n. But we can get into worst case scenarios where we have an O to the n because we have to search long strings of a table that aren't properly balanced. So again, this one's has several different answers, and explaining kind of the idea behind that and what goes into getting those level or those algorithms to run in that is would be beneficial to your answer here. Question 4, again, that's for you guys to answer. Thank you, and good luck on your final on Monday. If you have any questions, please email me, and I'll try to get back to you as soon as possible. Thank you.